If you write this finite Gromov products, they will cancel these things. This blue and red cancels, blue and red cancels, blue and red cancels. Only this red, and this blue survives. That's what I have written here. So observe that this is independent of the base point. So no matter whichever base point you consider, this it will be just the limit of this cross differences of points which goes off to these 4 points. That's how you see that this cross ratios are independent of the base point for visual quasi-metrics on the boundary of a Gromov hyperbolic space. I mean, good Gromov hyperbolic space. Geometric mean value theorem. This here what we see is if you consider a quasi-metric space Z rho naught, consider any other quasi-metric on Z which is Möbius equivalent, there exists a unique continuous function from Z taking positive values such that you can produce this rho in terms of this rho naught by this expression. So this gives you a prescription of constructing Möbius equivalent quasi-metrics from one quasi-metric. And this is the if and only if condition. So the family of Möbius equivalent quasi-metrics on Z are in 1-1 correspondence with respect to the continuous functions taking positive values on Z. Moreover, I call this the derivative, and this derivative satisfies the chain rule. Moving on, so from now on, Möbius equivalent quasi-metric will have a representative continuous function. I'll go to and fro between Möbius equivalent quasi-metric and continuous functions from now on. I mean, whenever I talk about them. Möbius spaces. So consider Z rho naught a quasi-metric antipodal space. We define the Möbius space associated to Z rho naught. This was introduced by my supervisor. So to be the set of all antipodal functions on Z which are Möbius equivalent to rho naught. Now this space I can actually consider it to be a subset of continuous functions on Z by taking log of those derivatives. So this set is same as the set of continuous functions on Z which satisfies this property. This property actually represents the antipodal property of the corresponding quasi-metrics which you can produce from this prescription here. I'm just taking log on both sides and getting this. And we equip this Möbius space with a distance which is just log of the derivative of one with respect to the other. And because of the chain rule, we have this, that rho sub tau sub rho prime minus tau sub rho, where this is the derivative log of the derivative with respect to rho naught, and this is the log of the derivative of rho with respect to rho naught. Now consider a good Gromov hyperbolic space X, rho sub X and rho sub Y be two quasi-metric on the boundary. Then they satisfy this property that you can get rho sub Y xi eta squared from rho sub X by this formula, where this B x y xi the Boseman cocycle, which is given by this limit. And this limit exists because of the boundary continuity. This is exists and unique. And so because of the uniqueness of the derivative of Möbius equivalent quasi-metrics, which you saw in geometric mean value theorem, this Boseman function is actually equal to log of the derivative of rho y with respect to rho x at xi. So for some x we can consider and take the base point O, we can consider the Mobius space on the boundary, Mobius space with respect to the visual metric on the boundary. Then this is a well-defined map because you take the point X in the space and consider the corresponding visual metric. Observe that this map becomes a isometric embedding because of this equivalence of log of the derivative with the Boseman function. So if you take the sup of the Boseman function, it becomes the distance between x and y. And this embedding is called the visual embedding. So what we see is if we consider a good Gromov hyperbolic space and take the visual quasi-metric on the boundary and consider its Mobius space, there is an embedding of that space inside the Mobius space. So this is a fact which prompted the study of Mobius spaces, this embedding. Essentially, you have isometric embedding. So let's try to, so one can try to understand what this space is like, this Mobius space is like. So this Mobius spaces have nice properties that given a quasi-metric antipodal space, Mobius space is associated to this quasi-metric antipodal space are proper metric spaces, which is isometrically embedded in the set of continuous functions on Z with the sup norm. These are unbounded spaces that there are infinitely many Mobius equivalent quasi-metrics on Z. Not only that, they are geodesic, that you take any two Mobius equivalent antipodal functions, you can actually join them by a path of Mobius equivalent antipodal functions. They are geodesically complete. Any geodesic can be extended by infinitely. They are contractible. Further, these spaces are good Gromov hyperbolic spaces, and the boundary of these spaces equipped with a visual quasi-metric based at that point can be identified with Z rho. So this is a result proved by Biswas in 2024 paper. And moreover, all the elements of this Mobius space will be quasi-metric. Now I'll move on from Mobius equivalence to this Mobius maps and isometries. So for xy good Gromov hyperbolic space, any isometric embedding from x into y extends to a Mobius embedding of the boundary. That is, that preserves the canonical cross ratio. And if f is an isometry, that is, it is surjective isometric embedding, then f, this little f on the boundary becomes a Mobius homeomorphism. So a natural question one can ask is, given good Gromov hyperbolic spaces, if you have a Mobius homeomorphism on the boundary, does there exist an isometric embedding of x into y? Or does there exist an isometry from x into y? This is called the Mobius rigidity problem. A classical fact is that any Mobius homeomorphism of the boundary of real hyperbolic space extends to an isometry of the spaces, and this fact is useful in various rigidity results, for example, Mostow rigidity, pattern rigidity, etc. And I would also like to comment that if you have a positive answer for Mobius rigidity problem for cat -1 spaces, then you will also have a positive answer for Mark-Lane spectrum rigidity problem. That's how it is related to this side of cat -1, the special case of cat -1 spaces and the Mobius Mark-Lane spectrum rigidity. So you see, this Mobius rigidity problem is comes under this lineage of problems where you have some information on the Gromov boundary. You want to understand the space, whether you can to what extent you can understand the space. So in general, Gromov hyperbolic spaces are not boundary continuous, and you have this visual metrics. They are not Mobius equivalent to each other. What you have is, at base, they are quasi-Mobius equivalent. And it's a well-known fact that if you have two visual roughly geodesic Gromov hyperbolic spaces and you have a quasi isometry between them, then it extends to a quasi-Mobius homeomorphism on the boundary. And in case you have a rough isometry, then it becomes a bi-Lipschitz map on the boundary with respect to the visual metrics. Of course, yeah. So Choudhury proved the converse. In 2010, he proved that for visual roughly geodesic Gromov hyperbolic spaces, a bi-Lipschitz boundary map extends to a rough isometry of the spaces, and a power quasi-symmetric or equivalently power quasi-Mobius map between boundary extends to a quasi-isometry of the spaces. And his result generalized the results of Bongstam and Bueller-Schroeder. But the thing is that in these cases, what they do is they construct a hyperbolic filling of the space, and that's a canonical construction, functorial construction completely. But their constructions are very rough. They won't give you back the Mobius structure on the boundary. So these theorems won't solve or their techniques won't solve you the Mobius rigidity problem. Some partial answers to the Mobius rigidity problem are due to Cournot in 1992. He proved that for any proper geodesically complete trees, any Mobius homeomorphism between their boundaries extends to isometry of the trees. Bourdeau in 1996 proved that if X is a rank 1 symmetric space of non-compact type with maximum sectional curvature normalized to equal -1, and Y a cat -1 space, any Mobius embedding from boundary X to boundary Y extends to isometric embedding of X into Y. Now, the hyperbolic filling construction, as I already told you, this Bong and Choudhury, what they did is they had the boundary, they constructed a graph which is Gromov hyperbolic, and its boundary becomes those metric spaces. So their construction is very rough. They won't give you Mobius equivalence on the boundary. So Biswas in 15 proved that if X and Y are proper geodesically complete cat -1 spaces, and if you have a Mobius homeomorphism between their boundary, then F extends to a 1, log 2 quasi-isometry, which is nothing but a rough isometry from X into Y, and the image becomes log 2 dense in Y. So here for the first time, we encountered a functorial construction of hyperbolic filling which recovers the Mobius structure on the boundary. So motivated by this result of Biswas, Beerer and Schroeder extended this to a Mobius equivalence of categories between proper geodesically complete trees and ultrametric antipodal spaces, where on this side you take morphisms to be isometries, and on this side you take the morphisms to be homeomorphisms, Mobius homeomorphism. So this functor is the boundary functor. So they showed that this boundary functor is equivalence. That is, boundary functor is an equivalence of category. So what they did is, they showed the construction from this reverse direction, from boundary side to here. But this was for trees. Later on, Biswas extended this equivalence of categories to a larger category of spaces. But before we go into that, we define the following: that let us consider X rho a quasi-metric antipodal space. A good Gromov hyperbolic space is said to be a good filling of this quasi-metric space if there exists a Mobius homeomorphism of this boundary onto the quasi-metric space. we denote this by this pair x comma f, where f is this Möbius homeomorphism. Example, Hn is a good filling of Sn minus 1 with half of the chordal metric. Naturally, any good Gromov hyperbolic space is a hyperbolic filling of its boundary. So the Möbius space is a good hyperbolic filling of its of the quasi-metric antipodal space to which it is associated with. And now I give order on the set of fillings of a quasi-metric antipodal space. I say that yg is lesser or equal to xf if this boundary map, boundary y from boundary y to boundary x extends to a isometric embedding of y into x. So finally, now I have arrived at the definition of maximal Gromov hyperbolic space. A good Gromov hyperbolic space will be called a maximal Gromov hyperbolic space if it is the maximal hyperbolic filling. By that I mean if I consider any other filling of its boundary, consider this boundary x equipped with this quasi-metric, then there is an isometric embedding of the space y into x. Examples, proper geodesically complete trees are maximal Gromov hyperbolic. Further, Möbius spaces associated with a quasi-metric antipodal space are maximal Gromov hyperbolic spaces. That is, these Möbius spaces are maximal Gromov hyperbolic fillings of their boundary, of the quasi-metric antipodal space. Moreover, if you consider the visual embedding, which I talked about before, it becomes, if you consider x to be delta hyperbolic, it becomes k times delta dense in the Möbius space. And this k is universal for all delta. If x is maximal Gromov hyperbolic, then this visual embedding is an isometry. So this number 2 tells you that any maximal Gromov hyperbolic space is of this form, mz rho. Further, this m boundary x is an injective hull of x. So injective hull is so before I say what injective hull is, so an injective metric space is an injective element in the category of metric spaces with one Lipschitz maps as morphisms. So a metric space X is called injective if for every metric space B and every one Lipschitz map A from F from A into Y, where A is a subset of B, there exists a one Lipschitz extension of this F onto this B. Further, I say a metric space is injective hull of another metric space if it is the smallest injective metric space in which it is embedded. So if this x into y is an isometric embedding into an injective space y, I say y is an injective hull if it is an essential extension. By that I mean if you take any other injective space, let's say W, and x has an embedding into W, then it factors through this I. Next, Biswas also proved that there is an equivalence of categories between pointed maximal Gromov hyperbolic spaces with morphisms isometries and quasi-metric antipodal spaces with morphisms Möbius homeomorphisms. So in this direction, you take x comma little x, and the functor is going to the boundary x equipped with the visual metric based at x. And in this direction, you take z comma rho, a quasi-metric antipodal space. And on the side of pointed maximal Gromov hyperbolic spaces, you take the Möbius space associated with that quasi-metric antipodal space with the base point rho. we'll see that this functor, this z comma rho going to mz rho described by Biswas is actually continuous. Now, here on pointed maximal Gromov hyperbolic spaces side, you can always consider the Gromov house of convergence, pointed Gromov house of convergence. But on this side, you don't have any convergence of that sort because these are not metric spaces as such. So we had to define a notion of convergence on quasi-metric spaces. So we call it the AI convergence. So consider between two quasi-metric spaces, an epsilon isometry is a map where it distorts distance by at most epsilon, and the image is epsilon net of the codomain with respect to this quasi-metric on this codomain side. And I say we define that a sequence of quasi-metric antipodal space AI converges to another quasi-metric antipodal space Z comma rho naught if there exists a sequence of epsilon n isometries from Zn rho n to Z rho naught such that epsilon converges to 0. And we denote it by this expression where AI stands for almost isometry. Now, this is just motivated by the definition of Gromov house of convergence for compact metric spaces. So, if rho n and rho are metrics, then AI convergence is same as the Gromov house of convergence of compact metric spaces. Recall that this pointed Gromov house of convergence for proper geodesic metric space are given by this that for every R, it is just the convergence of balls where you have epsilon and isometries between this sequence of balls with base point pn's into the ball centered at this limit space xp, and such that it fixes this base point. So what you do is you have for every r and epsilon, there exists a natural number n such that n naught such that for every n greater than n naught, there exists an epsilon isometry from this ball on around Pn into this ball around P. And also this satisfies that Pn goes to P. And this is our result that if you have almost isometry convergence on the side of quasi-metric antipodal spaces, then you have pointed Gromov house of convergence on the side of pointed maximal Gromov hyperbolic spaces. So in a way, this functor z rho going to mz rho is continuous. Now, a natural question one can ask is whether the functor on the other direction, that is x going to boundary x, is that continuous? So it is not quite clear. It's this functor is a bit subtle. So there is a convergence of balls which induces the convergence on the boundary, but for sorry, since you had convergence on the boundary, you had convergence on balls, but given convergence on balls, it does not it is not quite clear to us whether it induces the convergence on the boundary, because the geometry on the boundaries depends on the asymptotic geometry of the space. So we required a natural hypothesis. We assume that let us take the sequence of boundaries to be equicontinuous. So by that I mean for every for the family of boundaries, we take that for every epsilon there exists delta which only depends on epsilon, such that if you have xi eta in Zn such that they stay delta close, then their distance from any point in Zn stays epsilon close to each other. So observe that this is nothing but a proxy of the triangle inequality. So if you have this rho n's are metrics, then a a family of metric is always equicontinuous because of the triangle inequality. So we were able to prove that if you take xn, capital Xn, comma little xn, which converges, pointed Gromov-Hausdorff converges to another x comma little x. And if you assume their boundaries to be equicontinuous family of quasi-metric antipodal spaces, then the boundaries almost isometry converges to their corresponding boundaries. An application of this would be for cat minus 1 spaces. We have that the boundaries of cat minus 1 spaces are metric spaces because those are Bourdeau metrics, right? So automatically you have equicontinuity. So if you consider a sequence of cat minus 1, so observe that here I did not require maximal Gromov hyperbolic. I just needed good Gromov hyperbolic spaces. So this result, there is a trade-off that I assumed here good Gromov hyperbolic and I have this. So here if you consider proper geodesically complete cat minus 1 spaces, if the sequence proper Gromov-Hausdorff converges, then their limit also Gromov-Hausdorff converges in the normal sense of Gromov-Hausdorff convergence of compact metric spaces. This is, I mean, for me, this is the most exciting result because this is so clean. An application of application to cat minus 1 phi level quasi-metric spaces. So we say a quasi-metric antipodal space z comma rho is cat minus 1 phi level if it has a good hyperbolic filling by some cat minus 1 space. That is this z rho is Möbius equivalent to boundary of some cat minus 1 space. So we say that this if you consider Zn rho n a sequence of cat minus 1 phi level spaces, and suppose that Zn rho n converges to Z comma rho naught, another quasi-metric antipodal space, then this Z comma rho naught is also cat minus 1 phi level. Thus, we have that cat minus 1 phi level quasi-metric antipodal spaces are closed under AI convergence. Another problem of interest would be to understand the structure of maximal Gromov hyperbolic spaces, that is, how they look like. So, if you consider maximal Gromov hyperbolic spaces with finite boundary, then this maximal Gromov hyperbolic spaces, suppose you have boundary with cardinality n, then this becomes isometric to a polyhedral complex embedded in Rn, and it is a L infinity polyhedral complex, and with the finitely many polyhedral cells, each with dimension at most n by 2, and the polyhedral complex is given by attaching half lines to a compact polyhedral complex. So what happens is near infinity, my spaces, this maximal Gromov hyperbolic spaces, will just be union of rays. And a remark would be that if X is a good Gromov hyperbolic space with finite boundary, that is boundary continuous, proper, geodesically complete, then it has an isometric embedding into the Möbius space via the visual embedding. And from that, you have that X is again trivial near infinity. So any good Gromov hyperbolic space with finite boundary will be trivial near infinity. I'll skip the proof. So this is how maximal Gromov hyperbolic space with 4 boundaries look like. It's a rectangle with 4 antennas sticking out. And this is the picture. These are the pictures of maximal Gromov hyperbolic spaces with 5 boundary points. These are the 3 different structures you can get. Now these rectangles can squeeze and squeeze and become a line or whatever. So further, an application of this is that So before I told you that I needed to assume that equicontinuity on the boundary. Now, if you have this limit, you are taking this good Gromov hyperbolic spaces converging to x comma little x, and this capital X is a maximal Gromov hyperbolic space with finite boundary, then you can actually drop the equicontinuity and have the same result, that the boundary is almost isometry converges. So since you know that the boundary is finite, you get some control over the bound geometry near, I mean the asymptotic geometry of the spaces. That's how you get this almost isometry convergence. And since you given any maximal Gromov hyperbolic space, it is isometric to mz rho, and given any z rho, you can actually approximate it by finite zn comma rho n. So by this first result, that z rho going to mz rho is continuous, we have that any pointed any maximal Gromov hyperbolic space is pointed Gromov-Hausdorff limit of L infinity polyhedral complex xn's, which are maximal Gromov hyperbolic spaces with finite boundary. And the last thing which I'll be talking about is that you have finite maximal Gromov hyperbolic spaces. Now you have whole catalog of this shapes change. So I want to understand that if I change this boundary, this z rho, any maximal Gromov hyperbolic space with finite boundary is essentially just mz rho. So if I change this rho, how does my polyhedral structure change? So I define this to be the big Teichmuller space. Big Teichmuller space is the set of all maximal Gromov hyperbolic spaces, z comma rho, where z is fixed, a finite set, where I marked it to be mark the boundary points. Now I vary this quasi-metric. How does the space change? Now we have been able to show that a big Teichmuller space can be parametrized by a open simplex. So we have a nice parametrization by a open simplex of dimension m into m minus 3 by 2. So if I take m equal to 4, it becomes 4 times 1 divided by 2, that is 2. That's an open simplex of that's just a triangle. So in the triangle, we have complete stratification of this triangle by the structure of the maximal Gromov hyperbolic spaces. For example, the center of the triangle, it is just the tree with 4 antennas attached at one point. In these regions B1, B2, B3, these are rectangles with these antennas attached. Observe that this antennas ordering of attachment has changed, and along these rays going off from this center, it is it becomes trees with this where these rectangles have shrunk to this one line. So what happens is we have got a stratification of the space given by the combinatorics of the polyhedral complex structure. So a natural question one asks is whether a similar polyhedral decomposition of this big Teichmuller space can be given by the combinatorial types of the polyhedral complex for z greater or equal to 5, let's say. Thank you. I'll end my talk here. Thank you for listening. Any questions?
Yeah, thank you, Arka.
Yeah.
Do we have any question? Okay,
So,
I have some
yeah.
questions. Can you
Yes,
please
sure,
go
sure.
back to the Möbius rigidity slide?
Yeah. Yeah, sure. Right.
Yes. Okay, so basically, in general, if we have a Gromov hyperbolic space, let us say we have a proper geodesic Gromov hyperbolic space.
Hmm.
On its boundary, we have a class of this quasi-metrics, which we're
Hmm.
calling quasi-metric, like visual metrics.
Yeah, right.
Okay. Uh, so what I have understood is that what you're doing, basically, you are taking a space. So basically, now you're restricting your space to the space of boundary continuous spaces.
Right.
And then, so basically, in general, these two metrics, so in general spaces, in general Gromov hyperbolic spaces, these two quasi-metrics are basically quasi-symmetrically equivalent.
Yeah, right. They are
Yeah.
quasi, in fact, quasi-Möbius.
Yeah, I mean, on bounded, they are same. So,
Right.
yeah. So now what you're doing is you are taking boundary continuous space so that now your metrics are Möbius
Möbius
equivalent.
equivalent.
So that you can
Right.
talk about the Möbius structure there and
Right.
those things.
Right.
Okay. Okay. And then you're asking whether a Möbius map extends inside as an isometry.
Isometry. Right.
And you mentioned some result. Can you go back to that one? Like the earlier known results in this direction.
Yeah. So Jordi had this result that if you consider visual roughly geodesic,
Mm-hmm.
you have that any power quasi-symmetric or power quasi-Möbius map on the boundary
Mm-hmm.
extends to a quasi-isometry of the spaces.
Yeah,
And
but in this scenario, they are definitely not assuming that the space is boundary continuous.
boundary. No.
Yeah, because
Yeah.
because
Yeah.
it doesn't because that doesn't make sense.
Right.
Okay, and you said that their proof doesn't apply to this situation because.
Because what they essentially did was they took let's say I give you a metric space.
Mhm.
What you do is you construct a Gromov hyperbolic space such that its boundary becomes that metric space,
Mhm.
or the boundary is quasi-Möbius equivalent to
Mhm.
that metric space. That's what their goal was. So
So,
what they did is they took x and y.
Mhm.
Suppose you have a quasi-Möbius map between their boundary. They
Yeah.
constructed a functorial construction of a filling of their boundary.
Okay.
And then they said that my space X is quasi-metric to this filling, and on this other side, my space Y is quasi-isometric to this filling. And suppose you have a Möbius quasi-Möbius map on the boundary between this filling space and this other space that extends quasi-isometrically inside. So you
Okay.
have three, I mean, composition of three
Yeah,
essentially.
understood. Okay.
Yeah, that was their construction.
Mhm.
So what here in constructing this Möbius spaces, what you are doing is essentially is again you are functorially constructing it. But here the construction is nice in the sense that you get back the Möbius structure on the boundary. That's it.
Yeah. So ultimately, so it seems so. Okay, I think I have understood.
And the construction is quite clean in the sense that you just consider all Möbius equivalent antipodal
Mhm.
functions.
Yes. Yes.
And that is motivated by this fact that you have that if you consider the space X, it's the visual quasi-metrics based at those points, those are Möbius equivalent to each
Mhm.
other.
Yeah.
So that is automatically inside.
Yeah. I mean
So
that is the kind of.
yeah. So I consider everything, all possible.
Yes.
Let's say what happened to that space.
Understood. Understood. Yeah.
Turns out that space is Möbius equivalent.
Mhm.
I mean, that space is good Gromov hyperbolic, boundary continuous, and all that.
Yeah. Okay. Do we have any other question? Okay. So if not,
Acha,
let us. Yes.
Abhishek, I have one question for you. So,
Okay.
this Möbius equivalence and this quasi-Möbius equivalence,
Yes.
what is the relation between conformality and quasi-conformality in this side?
Uh, See, in general metric spaces and all these Riemannian spaces or non-Riemannian spaces, we basically call conformal as just one quasi-conformal because there is no definition of conformal in those settings. So we
Okay.
just call it as one quasi-conformal. As a conformal, we just assume or we mean it as a one quasi-conformal. But to talk about the boundary metrics being quasi-Möbius. So see, there's a concept of quasi-Möbius and quasi-symmetric, and
Right.
I guess they coincides on the bounded thing, on a compact thing. They coincide. So
Yeah, if you consider the space to be nice enough, they are just
yeah,
same.
they are the same. So now, once we have this two metrics, they are in general they are quasi-symmetrically equivalent. So basically, once these two metrics are quasi-symmetrically equivalent, you can define a quasi-symmetric structure on the Gromov boundary,
Okay.
and you can talk about quasi-symmetric maps there.
Okay.
Okay.
So what is the definition of quasi-conformal in the metric setting?
Okay, I guess that's the usual way to define. I mean, you take the balls going to some other balls, and you define kind of the maximal ball which is contains the image, and the and the and the s- and the minimal ball which is contained in that image, and take the ratio of it. Basically, it is
Okay.
kind of taking the ratio of the
Okay.
spheres you get.
Okay.
Major and minor axis. I guess you can see the paper of Hevnen and Koskela. That's the kind of
Is
fun.
this the paper that you are discussing? I
Yes,
mean,
yes,
I
yes.
I wanted to join, but every day at that time I am either coming back home from office or something.
Okay, that paper we are discussing. So that's the kind of
How far have you gone? Like,
not much. We are so since the proof of the main results requires a lot of things to understand. So I'm just first recalling the basic things like different kind of spaces and those things. So till now I have just discussed for quasi-conformal mappings in plane and notion of metric measure spaces. Yeah, that's it.
okay,
Yeah.
I'll see if I can join next
Okay.
day.
Okay, sure.
Okay,
Okay, so if we don't have any other questions, let us thank our speaker. Thank you,
thank
Arka.
you.
Thank you so much
Yeah,
for
you're
such a nice
most
talk.
welcome. Yeah.
Okay, we'll see. We'll see later. Bye.